What are the scientific challenges in moving from targeted to non-targeted methods for food fraud testing, and how can they be addressed? Spectroscopy case study. Food fraud has been documented in literature since the times of the ancient Greeks. However, in more recent times, food fraud has garnered much greater notoriety due to a variety of factors. The growing complexity of food supply chains and the substantially greater opportunities to conduct fraud across them. Food fraud often involves economically motivated adulteration, with those committing it aiming to increase profit margin by any means necessary with little regard for consumer safety. With the subsequent use of unconventional and in some cases non-food adulterants, which are unlikely to be detected using the conventional targeted analysis. This has brought about the necessity to develop non-targeted testing systems, which encapsulates the physico-chemical analysis of the whole food matrix, leading to the development of a food fingerprint, as opposed to targeted analysis where a known analyte is specifically screened for. In order to keep pace with those who perpetrate food fraud, there is clearly a need for robust and reliable, non-targeted methods that are available to many stakeholders. This research, carried out within the scope of the European Commission project FoodIntegrity, describes the implementation of spectroscopy, the analysis of the interaction between matter and electromagnetic radiation, using 3 different techniques for non-targeted analysis of food matrices such as beef, milk and olive oil. Key challenges faced by the research and routine testing communities are outlined, including a lack of guidelines and legislation governing both the development and validation of non-targeted methodologies, no common definition of terms, difficulty in obtaining authentic samples with full traceability for model building, and the lack of a single chemometric modeling software that offers all the algorithms required by developers. Authors' recommendations to address these challenges include: use appropriate, robust and reliable instrumentation. Develop and adopt guidelines or legislation to standardize language, development and validation procedures. Develop guidelines or legislation to outline sampling requirements for robust models. Try to include CRMs in model development and testing or validation sets. Sampling database should be fit for purpose and consist of at least 200 samples for each class. Spiked samples should replicate the industrial process as closely as possible. Concentrations of spiked samples led by intelligence. Use a cross-representative selection of authentic samples when preparing spiked materials.